This is section 4.3, number 17. It's one of the matching problems, and there's some substantial work to be done to figure out who goes with whom, and here we go. So as we look at the four graphs, here they are, the one thing that we can observe fairly easily is that graphs 2 and 3, B and C, graphs B and C both have period of pi, of 2 pi, I'm sorry, because we see that we have exactly one cycle, roughly in a 2 pi period, so we're going through one cycle. And here too, we're going through just one cycle in a 2 pi period, so this has a period of 2 pi. Whereas these guys go through, it's hard to draw with my pen, but you can see there's 1, 2, 3 peaks. So these have period of 2 pi over 3. This is a period of just 2 pi. This is a period of 2 pi over 3. This is a period of 2 pi. 2 pi over 1 and 2 pi. And again, you can see that there's 1, 2, 3 peaks, so that corresponds to 3 complete cycles of a sine or cosine. So as we look up here, the omega, here omega being 1, implies that the right-hand side, if we look at the equation, the right-hand side being omega t, omega being 1, the right-hand side is a period of 2 pi. And here we see omega is 2, that would correspond to a steady-state solution or forcing function, and therefore a steady-state solution with period just pi. And here we see with omega 3, we'd have a period of 2 pi over 3. So, so our only options for for 1 and 2, I'm sorry, so these guys can live here, and or here, and then 1 and 2, which will both have results whose period is just pi, will correspond to either C or D. Okay, and we're going to take the 1 or 2 case first. So we're going to try to decide whether one goes with C or one goes with B. Okay. The one observation in all these cases where we can make a distinction, so what's the difference between these two? Well, amplitude of the steady-state solution would be what distinguishes these two. This one has a noticeably larger amplitude, almost about 0.5. This one maybe 0.2 or something, we'll see. But this has a noticeably smaller amplitude than this one, and that's how we'll distinguish whether we're going with 1 or 2. So we go to the next slide. Okay. So here I've already laid out the work. In 1, P is a 5, Q is a 3, and of course omega we already decided was the 1. In 2 we've got P as a 1 and Q as a 3. When we plug in everything, here is our second order differential equation with our forcing term. Here's the other second order differential equation with the same forcing term. But we're going to do our complexification method, meaning that we're going to write this right-hand side as e to the it, and if we were to go ahead and find a solution, the solution would be the real part of our complex solution. So we're doing the same thing in both cases here. Okay. What we try is the complex solution a e to the it. So we have an exponential here. We try an exponential with an undetermined coefficient. Same thing here, same right-hand side, so we try the same complex solution a e to the it. Here's the first derivative, where just an I comes down, and here's the second derivative, where we have a minus 1 now, because when the second I comes down, I times I is minus 1. I didn't write that on this side because they are the same first and second derivatives. When I plug in, when I take my second derivative and I plug in here, I'll get a minus 1 a e to the it. When I plug in my first derivative, here's my first derivative into the equation, I'll end up with a 5 I, and here's my a e to the it. And when I plug in my my trie, which is this guy, I just get 3. I get a 3 a e to the it. So I've already factored out the a e to the it, and on this side we have a 1 e to the it. Canceling our e to the it terms, we're left with the statement that a times 2 plus 5i equals 1, divide by the 2 plus 5i, get a real number base by multiplying above and below by 2 plus 5i. The base is 29. The magnitude of a complex number is the square root of the number times its conjugate. And a with a bar on top is the conjugate of a in the complex world. That leads us to, when you multiply a number by its conjugate, you get the sum of the squares of the two components. They're both over 29, so that's 29 squared. We end up with 1 over the square root of 29, or 0.18. On this side, same idea. We have, we plug in, we collect like terms. A is 1 over 2 plus I, otherwise known as 2 minus I over 5, after multiplying above and below by the complex conjugate. The magnitude of this, using the same formula, is 0.44. And so this is the larger amplitude, 0.44 versus 0.18. And so, so this guy goes with the first graph. Let's just scoot back. I can't scoot back, but if you'll look back at the slides, you'll see that this guy, the larger amplitude, was, I'm sorry, the larger amplitude was B, so this guy must be B, and the smaller amplitude was C, so this guy goes with C. Okay, let's go forward one more time. Now we're going to address the two pictures that have a period of 2 pi over 3. So this is either A or D. So we're going to move forward and decide which of those two. Again, D has the larger amplitude. So D has the larger amplitude, A has a smaller amplitude. And that's how we'll decide who goes with whom. We go forward. I've already laid out the work. And we'll say the same thing a little more quickly. Here's what we're given. P is 5, Q is 1, and omega is 3. If I already write the right-hand side in its complex mode, instead of a cosine 3t, I write e to the 3ti. Here's our trie. We'll try something of the form of a undetermined coefficient times e to the 3ti, because that's our right-hand side. Here's its first derivative, where a 3i comes down. Here's the second derivative, where a 3i comes down again, and we end up with a minus 9. I plug into the differential equation, I plug in the second derivative, the first derivative, and the function itself, and after factoring out an a e to the 3ti, I'm left with a minus 9 plus 5 times a 3i plus a 1. Collecting like terms, I have a minus 8 plus 15i equals a 1. Here's the 1 it must equal. And again, that's after canceling out these guys that live on the, that can be canceled. A ends up taking on this ugly form. It ends up 289 is 17 squared, so when I find the magnitude of A, I find out that it's 1 over 17, or 0.058. Same thing on this side. I'm going to use e to the 3ti instead of a cosine 3t. I try a complex function as my solution. I plug in the first and second derivative. Here's the first derivative, same first derivative. Here's the second derivative. And I end up with a minus 9 plus 3i plus 1. Collecting like terms, a looks like 1 over 8 plus 3i, negative 8 plus 3i. Here it is with a real denominator. Same approach, its magnitude is 1 over the square root of 73, or 0.117. This is the larger amplitude, this is the smaller amplitude. Therefore, I can't go back and show you, but you can look yourselves, and therefore this is the picture that goes with, the larger one goes with D, and this one goes with A. Okay, that's it. Good luck.